Okay, so here's our 3D structure again. I've just color-coded and labeled the hydrogens to help us keep track of them. So what we're going to actually do is look at this molecule from the end, meaning I want you to think actually about standing on the left side of this molecule and looking at it in this direction. And if you were looking at it in this direction with reference to your viewpoint, this carbon is going to be the front carbon. This carbon is going to be the back carbon. What we're going to do is draw this in a different form that's called a Newman projection. Here's how we draw the Newman projection. We start with a circle that represents the back carbon. So I'm going to draw that in red. And then in the middle of that circle, I'm going to put a dot in blue that represents the front carbon. From there, I'll draw in my hydrogens. And I'm going to start with the ones that are in the plane. So hydrogen A is in the plane going straight down in reference to my viewpoint. So I'm going to draw it straight down, coming off of the front carbon. Then, coming off of the front carbon, we need to put hydrogens B and C. Those point angled upward to the left and right. So one will go here, and one will go here. Now we need to figure out which one is which. So this is a little tricky sometimes. So what I want you to do is think about actually laying down on this page. If you're standing here, I'm going to draw a little stick figure, and you're laying down on that page, looking at this molecule. What arm is going into the page? Your left arm goes into the page. Your right arm sticks out of the page. So that's your reference point. Hydrogen C is in the direction of your right arm. So hydrogen C goes on the right. Hydrogen B is in the direction of your left arm. So hydrogen B goes on the left. And then we follow the same procedure for the carbon on the back. The end-plane hydrogen, HD, is pointed straight up. Don't connect it to the central dot because that's the front carbon. Connect it to this large back carbon, HD. Then we have HE, which is back like your left arm, so HE will go on the left. And then HF on the right. And what you can spot is, for example, hydrogen C and hydrogen F are both on wedges. That means they're both on the same side. One's pointed upwards, one's pointed downwards, but they're on the same side of the molecule. Well, even in this Newman projection, they both end up on the same side. Just one's up, one's downward. Let's look at this in terms of our molecular model. So here is the ethane structure, just like we drew before. But now what we're doing is we're looking at it from this side. So if you're looking at it from this side, basically you're looking at it like this. It's a little hard for me to hold so you can see everything, so I hold it from the back. You're looking at it like this. So here's the front carbon, here's the back carbon. On the front carbon, we have, this would be hydrogen A. On the back carbon, hydrogen D. Here's B, C, here's E, and F. So this is the viewpoint you're basically drawing
when you write a Newman projection.
From here, we're going to take a look at what happens when we rotate around this front carbon. So we're going to leave this whole back carbon alone, and this bond here is going to be our rotation point, and we're going to rotate around that front carbon and see what happens. Since we're leaving this back carbon as is, let's start by just redrawing it as is. Now let's draw in the front carbon on the bond. And now, to put our groups in, I want to explain exactly where these atoms are ending up. So the rotation we're doing is we're rotating hydrogen A 180 degrees, such that it is up here in the plane on the opposite side of hydrogen D. So we're doing a 180-degree rotation around this front carbon. So now we'll draw in hydrogen A up in the plane. And now think about how that rotation affects the other two groups. So if I rotate this up 180 degrees, that's going to bring hydrogen B out and to the front. That's going to rotate hydrogen C here into the back. So now let's draw those in. Here coming out, we're going to have one group going back the other group. And now we draw HB going out, and HC is a group going back. Let's take a look at this in reference to a 3D structure.
Okay, so here's our molecule. I didn't have the exact colored atoms to color code them perfectly, but the purple atom is hydrogen B, the yellow atom is hydrogen C, and then hydrogen A is down here. So you can see C is pointed out, B is pointed back. When we rotate around this front carbon, what I'm doing is rotating hydrogen A, which was down on the bottom, 180 degrees to come up to the top. As we do that, this 180-degree rotation now brings hydrogen B, the purple atom, pointed out towards us, and then hydrogen C ends up going back away from us. So this is that conformation.
What we've basically done, if you think about your top Newman projection, is we've rotated this front carbon so that hydrogen A comes up 180 degrees to be in front of hydrogen D. So let's look at that on the model.
Right, here we are back with our original structure. We're rotating this front carbon like this. Now we have the 3D structure down here. If we view it from this side, here's what you're looking at. Basically, all three hydrogen on the front carbon are in front of the three hydrogen on the back carbon. They're eclipsing, is what we call this. It's an eclipsed conformation. So let's draw this, and what we'll find, we're going to leave the back carbon the same, but then we're going to rotate these three hydrogen on the front so that they're in front of the three hydrogen on the back when we draw the Newman projection.
I'm going to leave that up as a point of reference, but as we go to convert this to the Newman projection, remember we're looking from this left side, and what we're going to do is go ahead and draw our front and back carbon again. We didn't mess with the back carbon, so put the three groups on the back carbon exactly how they are up here in this original structure. So now when we draw in our front carbons, or our front hydrogen, really hydrogen A should be drawn right on top of hydrogen D. But that makes it really hard to visualize. So what we end up doing is skewing these hydrogen just a little bit. So for example, I'll skew this hydrogen A just a little bit to the side, like that. Then we'll do hydrogen B, and finally hydrogen C. Let's talk about just a little bit of terminology with these Newman projections. When the hydrogens are perfectly staggered, where the in-plane hydrogen on one carbon is 180 degrees from the in-plane hydrogen on the other carbon, this is called the staggered conformation. This is the most stable or the lowest energy conformation. So we often say that EREL, or the relative energy, is 0 because it's the most stable. Most stable, lowest energy. Those go hand in hand. For this conformation, if you were to measure the angle between two hydrogen, this angle is known as the theta, or the dihedral angle. And the dihedral angle in a staggered conformation is 60 degrees. Now if we come down to our other extreme conformation, where the hydrogen on the front are directly in front of the hydrogen on the back, this is called the eclipsed conformation. In this conformation, it's higher in energy because these hydrogen are kind of running into one another. Their electron clouds are bumping together. That raises the energy. The relative energy for this is 3 kilocalories per mole. And this happens to be the highest energy conformation of ethane. We're going to talk about conformational energies in a bit, but just to go ahead and clue you in, what's happening, every hydrogen-hydrogen eclipse raises the energy by 1 kcal per mole. And in this case, in terms of the dihedral angle, these hydrogen are directly in front of one another. So the dihedral angle is 0 degrees. What we've actually drawn here are the two extremes, the lowest energy conformation and the highest energy conformation. There's an infinite number of other conformations going from here to here where you can think about just incrementally moving or rotating this front carbon, going from here to here. We can't analyze every single conformation, so what we try to do is look at the extremes.